Welcome back to Calculus, gentlemen. This is going to be class number 7. This is our last class that is technically meeting before you have a quest on implicit differentiation and then go off and take your spring vacation. Remember, for implicit differentiation, so far we found the first derivative implicitly. We found the second derivative implicitly. And then we've also done things with those derivatives, such as writing the equation of tangent lines and normal lines. We have done writing the equations of horizontal tangents and of also vertical tangents. And in addition to that, we've also talked about finding the coordinates for maxes and mins and justifying if they're maxes and mins. Today we're going to go a little step further. And we're going to talk about whether we are finding an overestimate or an underestimate when doing linear approximation with implicit differentiation. In order to talk about over and underestimates for linear approximation with implicit differentiation, we're going to use one of the examples from the homework. Consider the differential equation dy dx is equal to 2x minus y. The part B from the homework that you had last night that was due this morning said determine the concavity of all solution curves for the differential equation in quadrant 2. Give a reason for your answer. Remember, when we talk about concavity, concavity comes from your second derivative. We can determine if your graph is concave up or concave down. So to find the second derivative, or d squared y dx squared, we're going to take the derivative of the derivative. If we know that our derivative here, dy dx, is equal to 2x minus y, we start with our first term. The derivative for 2x is just 2. Remember, this term only has x's in it, so we don't need a chain rule for the x. After you finish that term, we can go on to the next term. Note that this term is negative y. If we take the derivative of negative y, that is negative 1. But since this term has a y in it, don't forget that we need to use our chain rule, or dy dx. The derivative of y is dy dx. Since we do have an expression here that dy dx is 2x minus y, we can actually make a substitution here for 2 minus 1 times 2x minus y. That means that our second derivative here is going to be equal to 2 minus 2x plus y after we distribute the negative 1. If you're in quadrant 2, note here that your x values are negative and your y values are positive. Remember, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. In this quadrant here, the x values are negative and the y values are positive. So if we use those signs for the second quadrant, we know that the second derivative will take on 2 minus 2 times a negative number. I don't know what it is, but I know it's negative. And then plus a positive number for the y. We have 2 plus 2, and then plus, or some version of a positive number of 2, and then yet plus another positive. So this number here, if you're in the second quadrant, will always be positive, which is greater than 0. If your second derivative is greater than 0, that means that your graph is going to be concave up. It means it's going to look something like this. Since you have the derivative, okay, now we're going to move into the next part about writing the equation of a tangent line. We've actually already seen this in class 5 and saw it again in class number 6. If you want to write the equation of a tangent line, the equation of the tangent line comes in the form of y minus y1 equals m times x minus x1. Just use your point slope form. Note we already have our point, our x1 and our y1. That coordinate that we're using is negative 2, 5. The only thing we need here is our slope. So for the slope here, remember your slope is equal to your dy dx, okay? dy dx, this will be 2 times -2. Remember, this is 2x, and then minus y, or minus 5. If we simplify that out, that is -4 minus 5, which also happens to be -9. If we substitute this information, we're going to write the equation of the tangent line. That is y minus 5 is equal to a -9 times x minus that -2 becomes +2. There is the equation of our tangent line. If you'd like to, you can also solve for y. Y will be equal to -9 times x plus 2 plus 5. In part C here, they're asking you to estimate the y value of the graph if x is equal to -1.9. What they're actually asking is, let's suppose you have the graph at -2 and 5. And here's some point, and I don't know what the graph looks like right now because they didn't give us an original equation, but what I do know is that the graph will look something like that. So they're asking if x is equal to 1.9 or -1.9, okay, you want to estimate the y value at that point using that point of -2, 5. -1.9 would be close to about here. Notice we're not going to be approximating that point. Not going to be approximating that one. It's not close to the point -2, 5. What we're going to be doing is approximating the point that's close to where you wrote the equation of the tangent line. This is the one that we will be approximating, that coordinate there. Note again that that coordinate is very close to where we wrote the equation of our tangent line. When we want to do our approximation, we're going to take the equation of our tangent line, which happens to be y equals to -9 times x plus 2 plus 5, and we're going to substitute this value right in for our x. Remember, this is not an exact value for y, this is just an approximation. So y is now approximately -9 times -1.9 plus 2 plus 5. That means that we have -9 times 0.1 plus 5, or 5 minus 0.9, which is 4.1. So that means the point on the graph when x is -1.9 is approximately 4.1. So the coordinate -1.9 and 4.1, this is an estimation of a point that's on the graph. This is not the actual value. This is just an estimate of that y value. The question is, however, is that estimate an overestimate, or is it going to be an underestimate compared to the actual graph? Well, let's think about this for a second. Graphs are very helpful in helping us determine whether it's an overestimate or an underestimate. If you take a look at a graph that looks like this, notice that this graph is concave down. If your graph is concave down, if you take a look at your tangent line, notice that the tangent line will always lie above your curve. That means anytime you try to approximate the y value using your tangent line for the original graph, that value on your tangent line will always be above. So again, if our second derivative, if our d squared y dx squared is negative, if our graph is concave down, that means that your estimate will be an overestimate. We can actually consider this in the other direction as well. If our graph is concave up, okay, you can actually see here that your tangent lines will always lie below the curve. Notice any tangent line that I'm drawing to the curve actually lies below the actual values. That means that whatever we get from our tangent line as our estimate is always going to be an underestimate to the graph itself, to the actual value. So just recapping, if your second derivative is positive, meaning if your graph is concave up, that's going to mean that you're going to have an underestimate. We're going to have an underestimate from our linear approximation. So remember, we know that there's an actual point on our graph at negative 2.5. We are estimating that our point is negative 1.9, 4.1, and we're asking ourselves, is this number here an overestimate or an underestimate? If we want to know if it's an overestimate or an underestimate, we're going to have to use our second derivative. Our second derivative, d squared y dx squared. Recall from above that the second derivative here was equivalent to 2 minus 2x plus y. So we have 2 minus 2x plus y. We're going to have to use the concavity at the point at which we wrote the equation of the tangent line. So we have the second derivative. We're going to evaluate it at the point, again, that we wrote the equation of the tangent line from. This will be 2 minus 2 times negative 2 plus 5. This is 2 plus 4 plus 5, which is 9 plus 2, which is 11. Notice that this is greater than 0. Since it's greater than 0, that means that our graph is concave up. And if our graph is concave up, that means that our tangent line is always going to be below the curve, therefore having an underestimate. So this question here, the value that we found is actually going to be an underestimate. It's actually going to be an underestimate of the curve. It's pretty close, but it's going to be an underestimate.